detector. I was supposed to give a second lecture, which is essentially this on the PID, but I didn't finish this one. So I want to finish that because it's more important, and I take it also slowly. If I don't manage the PID, there will be on Indico. But I think it is a little bit important now that we go to the EIC detectors a little bit slower, and that you also get the concept. You don't have to understand every bit, but you know, the key concepts we should get into your head. Okay, so we talked about the EPIC collaboration, and then we started to talk about the detector. So this is kind of a drawing, a schematic drawing of the detector, how it is now. And I told you that's what we call the baseline, okay? So the tracking, and I told you, has to come very early. And all the trackers are here, what is marked in yellow. And they are in a field of, yeah, it's 1.7 Tesla. We can ramp up the field up to 2 Tesla. But we probably will run at 1.7 Tesla. We talked about this, about the strength of the field, how it is related to the resolution, but also that it, of course, costs you PT range, because the earlier they curl up, the less PT range you have in the low PT region. There are essentially 2 technologies only deployed here. And that one is silicon maps detectors, and I will mention that a little bit what this is. And the other is, I always call them MPGDs. That is micro pattern gas detectors. This is a whole group, a family of different detectors. They're pretty fancy. They were developed dominantly at CERN in the last 20 years, and there are many of them. And we are actually using 2. The one is called micro Arwell, and the other are called micro-mega, because they are French. So, and then, of course, PID, we have a really impressive amount of PID detectors. I think there's no collider experiment in the world which has such an impressive coverage in PID detectors like EPIC. We will have a high-performance stirk in the barrel. We have a proximity focusing ridge here in the backward region. That's backward. Remember, it's the electron going. We have a very fancy dual radiator ridge, which sits here. And we have time of flight, which sits in the middle and also here. We will talk about this in detail. And we have, of course, calorimetry. What is shown here in red is electromagnetic calorimetry. And if you remember, that has to come first. That is within the magnetic field, and then outside of the magnet, we will have the hadron calorimetry. In the backward region, we have an electromagnetic crystal calorimeter. We talked about crystals. Lead tungstate has one of the best resolutions we can get. It's a homogeneous detector. So this sits here. Then we have an imaging barrel EM cal. Maria is guilty of that. She works on this. This is actually so massive in terms of silicon usage that I don't know how many football fields you have in there, Maria, but it's big. Okay, so actually we have, interestingly, I was surprised. We always think about the LHC experiments of having, always these huge amounts of silicon. It turns out that actually EPIC has more square meter of silicon than any of the LHC experiments. Just to impress you. Okay, so then in the forward direction, this is where the hadrons goes. We have a finely segmented electromagnetic calorimeter and a hadron calorimeter. On the outside, we will actually reuse an existing hadron calorimeter. There, the resolution requirements, as I showed you, are not so stringent. So this is perfectly workable for us. So this is about the calorimeters. Now let's talk a little bit about the magnet. We call it the Markov magnet. We talked about it. It's a solenoidal field. It has to be a solenoidal. We cannot use any other shape. The coil is actually divided in 3 different models with 6 layers each. And this is mainly done to accommodate possible lengths because, the wires have to be wrapped around. And this is actually a cross-section of the wire. And you see these little strands with superconducting material. And then it has to be cooled. So here's a little bit the parameters. We have impressive 4,000 amps flowing through that. The temperature, it has to be cooled towards 4.7 Kelvin, so it means liquid helium. That's pretty much the most interesting thing. The rest is boring. So this is kind of the magnet, and what you see on the top is the entrance of the cryostat, which feeds the liquid helium and cools the magnet. Okay. So tracking, we talked about tracking. So one of the most fancy things which was developed over the years are the so-called pixel detectors. These have a very high resolution, and in the good old days, what you had to do was you had your sensor with pixels, and then you had your readout chip, your so-called ASIC, has to be sit on top, and it was bonded. It was very fancy bonding process. And many experiments still use that technique because they're a bit more radiation harm. But there were people who thought about, hey, why don't we put this all together in one monolithic silicon wafer? And this is called MAPS, which stands for monolithic. M stands for monolithic pixel sensors. And you can make them very thin. And now you can make them so thin that you can actually bend them, which is kind of mind-blowing, okay? And one of the guys who invented those was Winter from Strasbourg, and I saw a talk by him 20, 30 years ago. And he had this dream. He stood there, I remember, on the board and showed, how you could maybe bend them one time. And the time has come now. This is the first one which will be able to do that. And you see this here, how they kind of take it and strap it around this pipe. This is here actually 20 micron silicon, and you can bend it. And that's the idea. And that provides an incredible resolution, very close to the beam pipe. I told you that we had to go, unfortunately, a little bit outside of the beam pipe because they have to bake up heat the beam pipe to bake them out. Very unfortunately, but this is how it is. So the silicon vertex inside has 3 layers. These are these guys here. And that is a joint effort with the Alice collaboration because they are working on this, what they call the ITS-3. That is their new inner tracker system, and we are kind of collaborating with them on this. So the cool thing is, typically what you do, you have to take a flex board and then stitch these sensors on top, right? And that's a lot of work. And you have to glue them on, and you need, epoxy and God knows what. It's a lot of work. The ingenious thing with these sensors is that you take a wafer and you put many chips on the wafer. So they are wafer stitched. There is no need for an additional flex board or something. You have to imagine it's a single chip which sits, which has an extension like this. It's absolutely cool, and that saves you a lot of material, and it's just cool. It's just cool. So I think Ernst will come tomorrow. Next week, and we'll talk about this. The pixel size is 20 micron, which is important. Remember, I showed you the resolution, delta P over P resolution, which goes proportional with that. So that term is really important. The good thing is that it has a very low power consumption, so we might get a way of not water cooling it or liquid cooling it, but just cooling it with air. It's a little bit tricky because you have a 20 micron silicon layer, and you blow air. If it starts to wiggle, our momentum resolution goes to hell. Okay, so this is a bit tricky. Okay, and we talked already about the bake out. So then we have outer barrel layers, 2 layers, and there we cannot use these sensors, these wafer stitch sensors, simply because this is very expensive. So just imagine when you have a wafer, typical wafers, when you give them to the foundry, they are 20 centimeters where you put your chips on, okay? So if you have individual chips and one is broken, you just throw the broken chip away because, yes, the rest is good. But if you have a wafer stitch sensors and just one is damaged, you have to throw the whole wafer away. And that brings the yield of this down to kind of 40%, which means like you almost lose half of the wafers which are produced, and that increases the cost. Okay, so this will be standard sensors which means you have a flex board, and then on this flex board, you mount on staves these sensors. So now we come to what comes outside of these are the so-called cylindrical MPGD layers. And the first is a so-called micromega. And it's quite simple. I show you here a little bit the idea of a micromega. So you have a cathode on the top, and in between you have a mesh. It's a very fine mesh. And since it cannot touch the anode, you have these pins in between. And so if a particle comes through, this is filled with some gas. And here, in this case, it's argon CO2. And it, of course, ionizes the gas, and they then drift through the cathode. And of course, because there's a mesh which has potential towards the anode, you can here kind of, amplify the signal considerably, and then you read them out on your pads. So this is in principle the idea. The cool thing is that this is bendable, so you can put it, you bend it in a cylinder. So it's quite nice. So, and then comes the time of flight. So the time of flight, we talked about this, serves not only for low momentum PID, but it also helps a little bit in tracking. In the barrel, we have pixels which are longitudinal, elongated, because what really matters is only how well you get some fine, not some fine, not some fine, not some fine, not some fine, some fine. So the less cooling you need and the less material. Cooling, it's easy to talk about cooling, but cooling adds a lot of material. And Maria doesn't want any material in front of an electromagnetic calorimeter. So we have to reduce as much as possible. And this is one way that we make the pixel here a little bit larger. They have a fantastic timing resolution of 35 picoseconds. So that's quite impressive. Okay. So, and then, of course, I told you, we have to, I think you asked that we want to reach as much 4 pi as possible. So we have to cover also the forward region. And we are doing this by adding these disks here. And there are 5 silicon disks and 2 micro Arwell disks. So micro Arwell is a new fancy, also MPGD, which was, just coming up lately in the last 5 years, it popped up. It's produced at CERN. And very simple, very, very similar thing. But it also has a large gap here, which allows you a little bit tracking. So it's another MPGD. It has a pretty reasonable resolution in the order of 100 micron, which is, of course, not as good as the silicon with their 20 micron, or even better. But it's sufficient because it sits further outside, and we talked about multiple scattering. There is a point where, if the multiple scattering of a particle is so large, it just makes no sense to put super fine resolution there because it's anyway dominated by multiple scattering. It's just a waste of money. So, and it almost fulfills the requirements from the yellow report. It does so very well in mid rapidity. We have a little bit of problem in forward rapidities. There was a program, and I think Maria will talk about this, which is, I'm just finished, which is the measurement of diffractive J-psi production. And there you get a certain pattern, and the Fourier transformation from that pattern tells you how the gluons are distributed in the nucleus. Okay, it's a very interesting measurement, but it's very strong requirements on the resolution of the scattered electron. And we're just not getting there. And the reason is simple. We talked about this, right? Because we have to use a solenoid, and the bending power in the end caps is just not there. If I could put, 3 Tesla there, a dipole, this would of course work, but then the machine gets heart attack because we would bend the electrons, and we have synchrotron. So that's the price we pay. So, we can, unfortunately, we have other means. There are people, very smart people, working on ways to not improve the resolution, but still make the measurements, which I think is pretty cool. Okay. But otherwise, I said the momentum resolution, everything, you see the red curves are the requirements are met pretty much everywhere. There's one thing which makes us a little bit nervous, and that is the number of hits. If you are knowing, you saw these pictures from Alice or from STAR, where you have these hundreds of tracks, hundreds of points along the track. So what EPIC chose was to have less hits, but with very high precision, because we have silicon tracking, right? So the average number of hits kind of floats around, 8, which is providing high backgrounds, but we are a little bit nervous in the presence of high backgrounds, then your pattern recognition might be jeopardized. It doesn't look like this, but there is a little bit nervousness. But the pros is the resolution. The downside might be that we have to struggle a little bit with the pattern recognition, but time will tell. So now we come to colorimetry. The purpose, of course, is for the electromagnetic colorimetry, especially to detect the scattered electron and separate it from the pions. We improve the electromomentum resolution in the backwards rapidity with a very excellent colorimeter here. And we have to provide, and we talked about this, the spatial resolution of the two photons sufficiently to identify the decays of the pi zeros. If you want to show pi zero, you have to get the gamma gamma. They can be very close together. So here we have to think very hard to get this done. So we have here the electromagnetic colorimeter. Here on the left is a picture of the backwards one. I told you these are the lead tungsten crystals, which is probably the best crystal quality or you can get, and they reach something like 2% resolution. The crystals are 20 centimeter long. So we talked about this radiation length. This has 20 radiation lengths of the depth, and they are very sensitive for temperature fluctuation. So if the temperature fluctuates, your energy calibration fluctuates. And since you don't want that, you have to be a bit careful. Then you have the imaging barrel colorimeter. This is now, I think, 4 layers, Maria. We started with 9, and it was down to 6, and now we are down to 4. This is a chip which is called AstroPix. It's called Astro because NASA is kind of involved and engaged in this. And it was, of course, intended for space-based experiments. The sensors here are 500 times 500 microns, so a little bit bigger than the maps, which are 20 times 1020, as I explained. And they are interleaved with scintillating fibers and lead layers. And they have a depth of 17 radiation lengths. So not quite as much as here. But there's also not, I told you we are not too rich in radial space. And then we have what is called the sci-fi electromagnetic colorimeter in the forward region. And that's a pretty cool thing. You just take scintillating fibers. I told you sampling very often, helps you reduce the cost. So what you do here, you have these scintillating fibers, and then you have a tungsten powder mix, and you embed these fibers in this tungsten. So tungsten, of course, has a huge Z and A, so it's very highly absorbent. And but the particles which cross and go through the fibers then produce light, which we detected with silicon photomultipliers. So that is our colorimeters, the electromagnetic colorimeter. Then we have the hadron colorimeters. There's not too much to talk about. There is a new one in the backwards region. I mentioned that we will use the one from the S-Phoenix experiment and reuse them. We build a new one in the forward direction. Ulrich is mostly involved in this, and Yale. This is steel and scintillator. The silicon photomultiplier rate out. It is highly segmented longitudinal. And it has the whooping number of almost 600,000 silicon photomultiplier. I mean, these numbers go up easily. Quite impressive. Okay. So then we come about particle ID. And we talked about this. It's, in the backward and the forward region, one kind of wants to separate kaons and pions and protons in the range of 7, 8, 9, 10 GeV. That's kind of the ballpark. But the whooping demand is in the forward region, where all the debris of the hadron goes. And here we have to go up to 50 GeV. That's pretty tricky. And we have these 4 detectors. We have And I go quicker through that because if I might have some time, we might go through my PID slide. So here's a proximity focusing ridge, which is a very simple ridge detector. The fancy thing here is a new readout, a new photosensor, very fancy. Then I think this is an ingenious principle, which is a DIRC. This is also a ridge detector. This is because we don't have a lot of room, the only thing we can use in the barrel. And that gives us PID up to 6-7 GeV. And then in the forward region, we have this enormous dual ridge detector. And again, as I said, this whole thing is augmented by time of flight. So, and with that, we are thinking we could be done, but we are far from done. And that is exactly your question. It is not 4 pi, because our detectors end roughly only at a rapidity of 3.5, 4. There's much more. And especially the interesting physics is there. How do we get this? And there we have to go, of course, outside of the detector. And what I show you here is kind of a current setup. So here you see the EPIC experiment, but I just showed you the barrel. These are all both magnets, quadrupoles. Here are the platforms where the electronic will stand and supply it. And we can actually move this detector in and out of the hall, other than in pits like LHC, where they are kind of deposited deep down underground. You cannot move them. We can actually move them up. So, and here are the beam lines. The electron comes from the top. The hadrons come from the bottom here. So we have to equip the beam lines because we want to get to 4 pi. The first thing we need is the luminosity system. And we have to know the luminosity to a very, very high degree. And why is that? I assume that Maria will tell you that. We saw already, she showed you a picture of the structure function for F2. There's a structure function which is of a special interest for us. That is FL, the longitudinal structure function, because it is very sensitive, much more than it. To measure FL, however, you have to measure at different energies. And to measure at different energies, and you have to compare that then, you have to know the luminosity very exactly, because that gives you exactly the cross-section. So luminosity is bad, this FL will suffer, okay? The way you extract it is through something you might have heard is called a Rosenbluth extraction. Are you talking about it, Maria? Okay, we're talking about it. So it is important that we know the luminosity with the highest precision. And these detectors, we put some emphasis there, and they will sit here now out there far away. Then we have the low Q-square takers, and their main function is to detect the scattered electron very close to the beam line. Remember at the beginning when I showed you where the electron goes, that is the low Q-square section, or photoproduction, if you want, even down there. Q squares up to 10 to the minus 3. This is where it is. If you're interested in saturation physics, that's your detector, because that measures the electron which goes very much forward. Because we are crazy and we need all these detectors, in the backward region, we put detectors within the magnet. That's actually pretty tricky. I don't know if this was done so often before. It's completely insane because there's not much room. And of course, you have a hole, the cooling, everything will be tricky. But there we have tracking and actually 4 tracking layers right now. So this will be a tour de force. And then, last but not least, we have, of course, a 0-degree calorimeter, which those of you who work on hadron experiments knows that. So if the nucleus breaks up, if you have PA, there are neutrons emitted, and the neutrons are detected exactly here. And that will help you not only to distinguish between, for example, in incoherent, in diffractive events, to distinguish between coherent and incoherent. But if we ever have a chance to calculate an impact parameter, you know, I mean, where the nucleus meet, you know, where the electron meet on the side or in the middle, there is a slight chance that we might be able to do this by looking at the number of emitted neutrons. It will not be as great as in heavy ion physics, for example, but you know, we might have a shot. So, and at the end, we have what is called the Roman pots. and off momentum detectors. They are called Roman pots because apparently not because the Romans built it first, but because the University of Rome was instrumental in building the first Roman pot. So these are cool detectors. They are actually sitting within the beam pipe. And what you do is you have these cylinders which stood up, and then they move with a step motor. Essentially, the detector is closer to the beam. You want to stay typically 10 sigma away from the beam size, because this beam, our electron beam, has 2.5 amps that burns a hole in it. So you don't want that. So you stay away. But on the other hand, of course, you want to get as close as possible because that gives you a lot. So what that does is it detects let's look at diffractive physics. You have EP goes into the scattered plus the proton plus whatever. And that is the scattered proton. And the momentum transfer between that is called T. T is, from the physics point of view, a very important variable. So we have to measure the outgoing momentum. Right? And that is done with these Roman pots. So, where are we? Oh, yeah. Data acquisition. Anyone knows what a streaming data acquisition is? No, okay. Anyone knows what a trigger is? You know what a trigger is? Okay, so the streaming. So in a typical experiment, you have so-called trigger detectors which tell you that an event took place, a collision. Okay. These are very often detectors which are very close to the collision point or calorimeters and something. And that trigger has several levels. And the first level say we have a collision. And then it tells it all to the other. And then all the detectors start to read out that event until they're done. And then they're waiting for the next trigger. Now, if you're streaming, you don't have triggers anymore. That saves you the trigger detectors, but you take essentially everything. It's just, imagine you put a camera in there, it's like a video camera, and you continuously measure what comes out. That's, of course, brutal because the data flow is quite high, but we don't have so many tracks. So that's okay for us. The tricky part is that each detector, of course, streams its stuff out. And someone at the end, it's the poor guy who has to assemble all this into events again and build the events. So this is fun. I know that Alice has quite some trouble initially to get this done. So this will be fun. I don't want to go into details. It's just keep in mind, take away that there's a streaming readout. So the last I want to talk about is about integration. And this is a very dense detector. And we have to service those. And it's, very detailed plans how you do it. Once the detector is in the beam and something breaks, you cannot just say, stop, go in for an hour, take everything apart and fix it. Doesn't work. Okay. So how you take, for example, this detector apart, how it's moved out is quite a challenge. And there are many engineers thinking very hard about this. And of course, it has to be very much, as you see, it is integrated into the beam line and into the so-called interaction region. So this is all kind of very tricky thing, and a lot of time and effort is actually involved in understanding how to put all this together. Okay, so that was the end of my first lecture. So there are more talks coming. I am supposed to talk about particle ID. There is a talk about calorimetry from Brook. There is a tracking lecture from Ernst Sichtermann, and there will be a talk about polarimetry, which I didn't mention, by Ulrich Lecture. So my problem is that I need the next talk now. Can you do that? So I still have 50 minutes. This one, yeah. Okay, good. I will be quick. We talked about the requirements and you saw the table. I think I mentioned it again. Backwards up to 10 GeV, barrel with rapidity up to 6 GeV, forward up to 10 GeV. And by the way, and please remember that always in your life, what I will talk to you now. When we talk about 3 sigma separation, what does it mean? Okay, and it turns out that 80% of all physicists are cheating. They are not doing it properly. And that's okay. But you have to realize this. So if somebody says, oh, we have to separation of 3, 4 sigma, ask how it calculates this. So what is the reason? So you have two signals. It doesn't matter what it is. Some variable, and you have particle species 1 and particle species 2. Since the detector is finite resolution, they have a spread. The difference between those we call n sigma. Do we? So this is kind of how many people calculate it. They simply take the average. So they take the difference and divide it by the average of these two sigmas, which statistically is absolutely nonsense, as you know. Because what you have to do, you have to add them quadratic. This is what statistics teaches us. And the reason is, when we say 3 sigma and we do it this way, this is not what every statistics books tells you that this is 99.7%. It is not. Because there is a factor square root 2. So this is only 95%. So, and that can become, this can make actually quite a difference. So 3 sigma always sounds cool, but just please be aware if people mention that what that definition actually means. So, yeah. So let's come to the backward region. And I would like to start very quickly with the PF ridge. PF stands for proximity focusing ridge, which means it does not have a mirror. Remember, it radiates when it traverses a radiator. I talked about aerogel, lightest material in the world, pretty cool. So particle goes through it, and in this thin radiator, it emits Cherenkov photons at a certain angle. And so you will get a ring on some readout plane, and a pion, this is a pion, this is a KM ring, have different radii. So that allows you, if you detect them, to distinguish them, okay? So aerogel covers typically the region, from 1 to 6 GeV, and that is what it does. And you just you have to tune, and you can tune the refraction index of these aerogels a little bit. You tell the manufacturer to tweak here and to tweak there. As long as they keep it transparent, that works. So what we do with the aerogel, there are 3 bands. You see them here of aerogel. They're kind of tiled together. The vessel itself is a carbon fiber honeycomb sandwich. That is what pretty much everybody's doing right now, and it's filled with carbon. The really cool thing, I will talk about this, are the photosensors. Reading out ridge detectors is a tremendous problem, okay? In the old days, one used Stony gas, which takes light and transposes it into electrons. Stony was used in Vietnam for illumination of battlefields. US threw millions of tons of battlefields in Vietnam. Stony is a nasty stuff. So we used it in my first experiment in Ne45 at SPS. You don't want to use it. There are other experiments which use cesium iodide. Cesium iodide is very sensitive. So light falls on, creates an electron. You measure, then you amplify the electron, you measure it. Cesium iodide is just terribly difficult to handle, because the moment it sees some humidity, the moment it sees some oxygen, it kind of loses its capability. So transporting, manufacturing, moving it around is a bit tricky. So this new thing is called HRPPDs. You need 68 sensors, and all they will sit here. That's roughly the size of the detector. And let me talk a little bit. The last thing I'm maybe doing today is talking about photosensors. The number of Cherenkov photons is not great. Typically, these detectors produce around 10, 12, that's it. You cannot afford to lose many of them. So you need high efficiency. And EPIC, I mentioned, also needs a very low material budget. But what also matters a lot is the magnetic field and the radiation, which is especially true for the 2 ridge detectors, the PF ridge and the D ridge. So we have a field strength of almost 1 Tesla. So the standard photomultipliers we use, I showed them at the beginning, you cannot use. I mean, they go black in the magnetic field, just won't work. You can use silicon photomultipliers. They kind of work well in the field. The D-Rich is using them, but they are notoriously sensitive to radiation. The D-Rich goes through a lot of efforts to kind of mitigate this. What comes out there is the so-called multi-channel PMTs, LAPBDs or HRPBDs. These are things which were actually produced in the context for the Dune neutrino experiment from high energy physics, but then when they switched to a liquid argon TPC, they dropped this effort and it was picked up by us. It's now done by a company. What it is essentially, you have these multi-channel plates, which you might know from night vision, military night vision instruments and something. They enhance light substantially. So the way is very simple. You have an incoming photon. It goes on a photocathode and is then transformed to electron. And they go into these channels here. So you have a potential. And so they go through here, they are amplified. And then at the end, it's an anode gap, and they end up on a pixelized detector. So they come in the package of 10 times 10 centimeter. Cost $50,000 a piece, which is actually cheap. There's worse things. But they have a fantastic spatial resolution of 1 millimeter, and they have an enormously good timing resolution, 15 to 20. So that's pretty cool. And that allows you kind of to really work in tiles. So this is that will be the first rich detector which uses HRPBDs. That will be very cool. And they work. This is looking really good. So this is the homogeneity of one of these HRPBDs. You see a little bit the structure, but that is good enough. The single photon timing resolution is really stunning. 20 picoseconds is probably the best which was ever measured. And you see here, this is the electron-pion separation. This is 3 sigma. That's the real 3 sigma, by the way. And here's 3 sigma for the pion kaon separation. And you see that they come out to HeV here, and we can separate electron from pions up to 2.5. Oh, that's pretty cool. Works. So now we come to the forward region, and I know that some of you work on the dual ridge, especially if you're from Italy. You cannot avoid the dual ridge. So they have to provide this continuous PID up to 50 GeV. And, we talked about this. You can only do this with 2 radiators. So what you will do is the proximity focusing enrich. We talked about this, where the radiator is an aerogel. And the other is a gas. But if you use a gas, you have, of course, an enormously long radiator. So you don't get this nice proximity focusing ring, but you would get just a blob. In other words, you need a mirror. This mirror kind of reflects independent of where this direct photon on the track is emitted on a very precise ring. So that's why you need a dual ridge. They have a moderately high magnetic field where they have to operate in. The photons detector sits somehow here in the back. But what is unfortunate is that the angle of the magnetic field is such that no other photodetector than a silicon PM works. It's not very often, doesn't matter really only where the magnetic field strength is, but what is its direction? And the direction is not optimal. So we have to go to silicon photon sensors, which are absolutely indifferent to any magnetic field. And of course, it is very, very limited in space. So that's why they have to go to a curved detector. This is how the detector layout looks like. It's also carbon fiber strengthened with reinforced polymers. This is, by the way, here a picture of the aerogel. You can see how these aerogel blocks feel nicely. So now we come to the real fun part. What's the problem with silicon PMs? And that is radiation. So they need to cover 3 square meter with silicon sensors. The sensors have 3 square millimeter pixel. This is a picture of one. Okay. They have a great single photon detection. They have high efficiency. They have excellent timing resolution. They're insensitive to magnetic fields, but they're not radiation tolerant. And what that means is that they produce a dark current, which means essentially de facto they produce your signals, which aren't there. And that is enormous. This is kind of like 50 kilohertz per square millimeter. Look at this plot. That is the integrated luminosity. This is what the machine provides, right? You run the machine and you integrated luminosity. And that is the dark current rate in hertz. The 300 kilohertz is that what we maximum can afford. You have to understand that DIS usually has very few particles. There's a scattered electron and maybe 4 or 5. It's not like heavy ion or P collision where there are hundreds of particles. So in that sense, you're good. The problem is if you have dark currents rate, that your data rate, which you're streaming out, is completely dominated by distance. So you have to reduce that. And the way you do that is that you operate the detector itself when it runs at low temperatures, around minus 30 degrees Celsius. So it's pretty freezing cold. But you cannot avoid having radiation damage. There's nothing you can do. So the idea is that you do some annealing. That means that you actually heat it to very high temperatures. And that actually fixes the radiation damage. That's really cool. But they want to do it in place. So now you suddenly have someone who says, hey, I want to put a poster oven in the middle of your detector. You say, oh, thank you. And how are you going to do this? So this is pretty tricky. So the first question is how much actually do they want to heat it up? And they did some tests. They did annealing from 100 to 175. And it shows you here, that is essentially the fraction of damage. And you see once you reach 175, you don't do much anymore. It stays pretty much constant. So 150 might be good. And there's another reason why 150 is good, because they tested this in the oven. And when they go to 175, you see the sensors turning yellow. That's not healthy, okay? So if you anneal it to 175, there seems to be kind of the limit. So what we want to do is we want to stay at 150. That's probably the thing. But it is a tour de force, and there's a lot of R&D going on, especially at INFN. And I like this plot. This shows you the evolution when you research and develop and make progress of a detector. This is how the different stages of the electronic. This is how the final module, that's a drawing of the final model, how it will look like. But you also see the output, right? I mean, the beginning, you're glad. You see a couple of pixels, and there is big joy in the test beam control room. And then slowly, as you progress, and now you can see perfectly these two rings. That's really cool. So we are getting there. But again, the dealing with the radiation damage of the silicon PMs is quite tricky. And it does what it's supposed to do, right? Here, that is in the forward region. That is from 1.5 to 2, then from 2 to 2.5. That is from 2.5 to 3.5, so very close to the beam line already. And you see what the aerogel does. That's, again, the 3 sigma, 4 sigma lines. And you see that the aerogel covers you up to 10 GeV. But already there, the gas kicks in. There is quite some overlap. And then the gas gets you actually really out to very high, here to 30, here to 40 with 3 sigma, and here even further. So this is just great. So that seems to work. These are simulations, of course, but supported by test beam results. So this looks pretty good. There is, and that is the last slide I want to show you, unfortunately. There's a little bit something we have also as we are physicists, but we are also living in a society which is struggling with global warming. And there are many gases, apparently, which are not very good for the atmosphere and promote global warming. And unfortunately, the gas which is in most of these rich detectors is in these gas-rich detectors is C2F6. That's the carbon fluoride. This has a warming power. This is the global warming power index. CO2 has 1. C2F6 has 10,000. Okay, it's really nasty. what that means is that more and more countries are banning it. Its use. Remember when we went through this fridge problem, certain kinds of freons we're not allowed to fix the ozone hole. And we are running into this problem slowly. There are experiments at CERN who need them. There's only, for example, in Europe, one company left who manufactures that in England, and they ask for a fortune because they are the only one. You know how it goes, right? If things get rare, things become very expensive. I think CERN at the moment is collecting as much as they can on the market for CMS, which uses some of those. What that means for us that we need a closed circulation system, so nothing gets out, so it's just circulated and recovered. That's a pretty tricky system. There is a way out. And we could replace that fluorocarbons by argon, which would be great. But we have to pressurize that argon at a few bar. Okay? So now you have a $500 million detector and you put a 3-bar metal vessel in the middle. And all security and safety people freak out. And especially to keep 3 bars, which is a lot, you need a very strong vessel. And that is, of course, not a lot of material, which we don't want. So there's an engineering challenge. There's R&D projects going on. It's honeycomb. So how can you make a 3-atmosphere, 3-bar vessel with that structure? And then you have to get it through safety. Because if that thing blows up, then your detector is certainly, more than damaged in the middle. So this is just something, it shows you that we are also thinking of these things, which has, of course, an environmental impact, but also, I think, the cost impact. Okay, so what I will not show to you guys is I have to stop, right? Yeah. The Dirk, Dirk was actually a cool thing. I have to mention that because I thought this is cool. So the Dirk is I goofed up. Can you go back? Go to this slide here. So the Dirk is also a Cherenkov detector where you go through these bars and the Cherenkov light is reflected and then expanded here. Long story, but these bars are pretty expensive. But it turns out that there's an experiment which had these bars, which was the Baba experiment at SLAC. So we asked them if we could have this stuff, and they said yes, you can have it. So it took quite a while to get it. But the problem was to get it. So this is, imagine you have to go from the West Coast to the East Coast with a glass of water on your head without spilling it, okay? This is roughly what that was, because these are crystals. Their surface flatness is in the Armstrong region. It's insane, right? So they have to transport this from the West Coast. So first of all, they picked a low altitude way. So they had shock absorbing foam. They had hydraulic shocks, they had air shocks, they have shock absorbing donuts, and they have an air ride with a temperature control truck. So they went all the way. And the tricky thing is this thing here is a setup. It is crazy. I mean, there's a kid. There's one protection mechanism on top of the other. And you see they had to stay below 1G and they managed it, except here. I forgot what happened here. but otherwise it was pretty cool. So they managed it. The bars are now taken apart at the Jefferson lab and they seem to look pretty good. So that was an exciting thing. So these are fun things which you have, as an experimentalist, you have to deal with at times. So this is fun. Okay, thank you very much, guys.
Yeah. For questions, so go ahead.
With the data acquisition system, especially in the triggers.
So again,
with that system, I'm wondering how you are gonna you're not planning to use triggers as you said.
No.
Okay, how are you planning to handle or sort this all of events that are not interesting in
you mean okay.
So
when I say no trigger, I mean in standard Dante mode.
Yeah,
So yes, so that needs some special attention, but this is actually not so complicated. But you don't need the traditional trigger system, but they will. So what you need, for example, is pedestrians or, so
Or FPGAs or something.
yeah, so there are, especially if you're not running, there are runs you have to do to kind of set pedestals, determine certain thresholds or something. These are special runs which the shift crew has to do regularly, once a day or every couple of hours. And then the system adjusts to that. Especially pedestals are important. What means pedestals? You have millions of channels of a detector, and they all fluctuate a little bit. And sometimes some of these things went a little bit more crazy than the others. Temperature-wise, it's a bad day, it's Tuesday, God knows. So, so you have to zero suppress them. But to zero suppress them, you have to know the pedestal. What is the average value, right? So if they are then whatever, such and such millivolt higher, and then it's a signal. If not, you have to suppress it. But you have to set these thresholds. These are special runs which are having to take. And yes, there you need a kind of special setup. You can call this semi-triggers if you want. So it's, if you say not triggered, we mean in standard running mode, the system is not triggered. Yeah.
Time of flight. Why there is no backward TOF?
Why there is no?
TOF has two parts, parallel and end gap.
Yes.
Why, like, that is towards forward side, right? Backward, there is no TOF.
There is.
Backward end
There
gap.
is.
Ah,
There is tough. Gotcha. So, yeah. So the time of flight, as you mean it, is of course the this one here, right? Which has the forward time of flight and the barrel time of flight. In the back, we had to remove it because the AC algorithms added a lot of material, which was not nice for the electromagnetic calorimeter, which is key in determining the energy or the momentum of the electron. And in addition, it was heating, and it was not heating constantly. There are always fluctuations. And I told you that tungstate crystals do not like temperature fluctuations. So the decision was that we take the one in the backwards region off. However, the PF-rich has HRPBDs, and these HRPBDs also serve as time of flight. Interestingly, they are even better than AC algorithms because they have, I showed you, 15 to 20 picoseconds, while the AC algorithms have in the order of 30. So there is no problem. We have backwards, and this is actually an important question. Because we always talk about how great it is and how precise we measure the time. But what we are interested in is actually the time of flight. And that means there has to be a start time and an end time. And the time of flight is the difference between those. So we always focus on this, but how do you get to zero? How do you know when the event actually took place? So, and one thing you can do is, if you have 4 pi all over the place, you can actually bootstrap yourself. Think about it. Sort of homework for you guys, how you can do this. But the moment you have full coverage, you can, by this, if you measure pretty much all the particles, you can actually determine when the start time was. Then, of course, yeah, and this is also why, because the HRPBDs in the PF-rich, they also give you kind of a very good T measure. You can also use the identified scattered electron. Why? Because the scattered electron is so light, it always has the speed of light. You know the velocity of it. So if you have the electron, you know the flight path, you can calculate T0. And there are also ideas to use the beam crossing. We talked about the crab crossing. And this is pretty tricky. That works very well, at least in simulations, we don't know. So these are kind of ways of calculating T0. It doesn't help you, again, if you have T measured to whatever picosecond, if the T0 resolution is 50 picoseconds. Okay? They have to be both very good. You have to put some effort into measuring really both. And yes, so that's why we have the HRPBDs in the backward reach, which is the time of flight.
With the HRPPDs, Is there an alternative for if they,
They don't work? Yes.
no, if they don't get produced, like if it doesn't work? Oh, yeah, it doesn't
Yeah.
work out.
Yes, there's a fallback solution. Which I don't know. They are called MCP-PMTs. There were two companies in the world who made them. These are also multi-channel devices. They have, pixels like a chessboard. There were two companies, Photech, Stony. One stopped making them, and the other we ordered one to test, and we are waiting for it since a year. They're not managing it, and the reason apparently is that their MCPs, these multi-channel plates, were produced in Russia, and they're not having access to it. So, they certainly will find other manufacturers, but this is a thing. And talking about expensive, they are expensive. They cost $15,000 a pop, and they are tiny.
They're not gonna be affected by the magnetic.
They're not affected by, yeah, we did test, there was R&D. They are not too happy. I think over 1 Tesla, but below they are kind of okay. But again, they are really expensive, and we are not believing that the company can actually provide it. At least not at the moment. There's a lot of shouting going. By the way, we are already, so I told you that, I think, so that the project is divided up in different steps from the Department of Energy, and we are already at a step where we can hire, or we already bought and ordered things which are long-term procurement. For example, we talked about the lead tungstate crystals, which are important to measure the electrons in the backward region. The company in the Czech Republic can produce 100 a year, roughly. That's the point. But we need thousands. So we better start early. So for the next, 5, 6, 7 years, this company will ship us whatever they produce. The same is actually true for the superconducting wires. It turns out that magnets like ours need so many wires, so much, length, that we have to order them right now, and the company has to keep sending them. So at the end, we can assemble them. I think it was impressive at LHC when they built the LHC magnets that they essentially used 3/4 of the world production of superconducting wires. Okay.
There are no other, let's thank Thomas again. So break for lunch. We'll gather at 1 o'clock again. So have a good lunch. So.
Are they teaching?